So yesterday we were discussing what are bandpass signal and what are baseband signals. So this starts at 3 p.m. and yesterday what we had discussed that if we have two low pass signals GIT and GQT that can be pressed as a complex valued signal G tilde T, then how to create a passband signal GT out of these. Fine. So this we had discussed yesterday. Today, what we'll do is that so the question is that the question that we'll try to answer. Question that we want to answer. Oh, sorry, answer is misspelled. The question that we want to answer is that yeah, given GT, can we retrieve GIT and GQT? So this is the question. So any guesses? Guys, can you hear me?
Yes, sir.
Yeah, so great. I thought I was just simply writing and not audible. Yeah, great. So since you can hear me, any guesses on this? How do we do this? What I'll tell you is that I'll just correct the T's. My T's look too much like plus signs. I realized it later yesterday. So yeah, guesses on these? Given GT, how do we extract GIT and GQT? They are orthogonal, right? So actually GIT and GQT are not orthogonal. Cos 2 pi FCT and sin 2 pi FCT are orthogonal. So I hope you understand the difference. But yes, we'll be using this property that cos 2 pi FCT and sin 2 pi FCT are orthogonal. More guesses?
So we can multiply
Multiply what with what?
g of t, like using the orthogonal property only. We will multiply g of t with cos in
Yes,
order to get
yes, yes, yes.
gi
So let's
and
say
sin.
YIT, or let's say Y1T. Why, why prejudice you? Oh, so the eraser, yeah. Say Y1T equals GT cos 2 pi FCT equals cos square 2 pi FCT plus, or minus actually, minus GQT cos 2 pi FCT sine. Fine. Now this equals GIT by 2 1 plus cos 4 pi FCT minus GQT by 2 sine 4 pi this. So we have this now. Anyone except Shubhashish? Yeah. Anyone except Shubhashish? Try.
Sir,
Yes, Samarth.
in that GT expression, like the original expression, we can put 2t. So like put t is equal to like 2t. That can help.
T. So how will that help?
Okay, okay, sorry, sir. I thought it would help by making it cos 4 by
No,
FCT.
no, 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 no. No, that's something totally different. Something. No, Shubhashish. At least for now. I'll. Sarit, tell me.
So we can do low pass filtering on the resulting expression. So
Exactly.
the uh,
Yes. Yes. See, we know that, or in the last lecture we said that GIT and GQT are low pass signals. Fine. So what this looks like is, or if I look at the spectrum of this thing, okay, I'll use this. Okay, if I look at the spectrum of if I look at the spectrum of this GIT, then so Y1T. So this is the magnitude spectrum of Y1F. So this is GIF by 2. This is two FC. This is around 0, and this is around minus FC. Right? So minus 2 FC, sorry. Fine. Now this is, so this gets added. GQF by 2 gets added at these 2 points. Actually, this is
So
minus.
there should be some subtraction.
Yeah. So yes. So here you'll get here you'll add minus GQF. In the on the left hand side, or and in the negative frequency, you'll be adding minus GQF. On the right hand side, you'll be adding GQF because sine and cos. Okay, sorry, again. So this should be minus and this should be plus. Sorry, twice. So GQF by 2 and GQ minus GQF by 2, because so balancing the signs, you get this. This is fine. So anyway, these don't matter, because say if we now have low pass filter, say this goes from minus W to W with pass band greater than W but much less than 2FC, with this filter having an impulse response HT and a frequency CY, frequency response HS. Fine. So I can now write so I can draw, say these are the filter, this is the filter bandwidth, and this, so this is what it is allowed, and let's say y bar 1t equals yt convolved with y1t convolved with, let's call this h1t as well, because we'll have to deal with the sign component. Okay, so this will work. So actually this h is sufficient. Yt, and this is so yeah, this is ht, and we get simply via frequency domain operation. We don't show that in time domain because in the time domain this will be a disastrously big operation. Git by 2. I set the gain of this filter set the passband gain of this filter.
Sir,
Yes.
so where are you writing this? I can't
Uh,
see this on the class notebook collaboration space.
yeah, so it won't be available in the class notebook collaboration space. You want to access it there?
Sir, no, it will be accessible once you post it.
Yeah,
The
once
note.
I post it. Actually, what happened was that I realized that if someone of you accidentally changes something in the notes, or accidentally
Yes, sir.
deletes some
Yes.
part of the notes, then the collaboration space is not a good idea.
Yes, sir.
So what I am doing right now is I'm posting these in my private teacher space,
Okay, okay.
and once the entire class is complete and I've corrected the notes, etc. I don't correct the notes, but still, if I find something additional for the notes, etc. So once the class is complete, I'll share the notes with everyone.
Okay, sir.
So these won't be live updated in your notebooks. So for live update, take your own. Actually, it's a for mathematics type of courses, it's a good idea to take your own notes. Yeah.
So,
Yeah.
there's one question. Should it be pass band gain or low pass gain?
So when we talk about the filter, the pass band is the band that you allow.
Okay.
So whatever band is allowed for that, if I keep the gain to 2, then y1t simply equals t, which is what I wanted. Similarly, I'll
So,
move to that.
wasn't there another method?
This is the simplest method. There's another method. I'll come to
Like
that.
integrating it over the time period would also provide us with GI of t.
Integrating over the time period won't provide you with GI of t, because that way, let's do it. Actually, a low pass filter is an integrator. The practical implementation of a low pass filter is an integrator. I agree with
Yes.
you.
Yeah, the capacitor and resistor combination only.
Yes, but let's see what you are proposing.
Okay, sir.
So, because there's more to a low pass filter than a simple integrator, or a higher order low pass filter would be better, because an integrator is a first order low pass filter. You have heard filter orders, right? You have heard of filter orders.
Yes, sir.
Yeah, so an integrator would be a first order low pass filter. So this is actually a good point. So let's discuss this in detail. Just that these pens today are, yeah. So an integrator is an order 1 low pass filter. So when I think of a low pass filter, what I see, or when I generally talk about a low pass filter, this is what I imagine, right?
Yes,
But
sir.
once you say that you want an order 1 low pass filter, you cannot have brick walls. So these brick walls improve with the filter order, or the quality of the brick wall improves with the filter order. So an order 1 low pass filter would look somewhat like the response of an order 1 low pass filter. The selection of pens is somehow delayed today. So midway this can change to red. Yeah, this has changed to red. So this is what an order 1 low pass filter would look like. So one thing you see, the clearest thing that you see is that the frequency response of the signal is distorted, right? Now
Yes.
let's look at the direct time domain implications of using this integrator. So where did here are the equations. These had disappeared. Yeah. So let's say we had this y1t is git plus all this stuff. So y1t equals t by 2 plus git by 2 cos 4 pi fct plus, sorry, minus gqt 2 sine 4 pi fct. Fine.
Yes, sir.
So I integrate this over, say, let's talk about a signal. So the selection of pens is somehow misbehaving today, but it's okay. It's serving its main purpose. So let's say I define a constant z equals 0 to t or 0 to 1 over fc. 0 to t equals 1 over fc. This is fine. y1t cos 4 pi fct dt. So this is what Shubhashish was proposing, right?
No, sir.
Then
If there should be G1T times cos of, because already we have the Y1 in required cos and sine forms, right? So
yes,
if we integrate it on the order time period, the cos form would become 0 and the sine form would become 0. We would only have GI by 2 times the time period.
yes, and we want to extract gi by 2
Yeah.
anyway.
Yeah, so if we wish to add extra GI by 2, then we will just be dividing it by the required time period.
But there's a problem.
So where it is?
The problem is that see, once you integrate it over a time period, you'll instead of a function, you'll get a number. You want a
Oh,
function of time,
yes, yes,
right?
yes, sir.
And what you will get instead is a single number. So you'll and those will be actually the samples of GT. Some weird sampling of GT. You'll have to do a whole. You have done some basic mathematics of sampling. You know how complicated it is.
Yes, sir.
Yeah. So you'll have to get, because now it's a sample which is averaged over a cos 2 pi fct kind of a thing, you will get something even more ugly. And you will get a series of samples. You won't get a continuous signal.
Yes, sir.
So in essence, what you are saying is right. Just that instead of this frequency response, this red frequency response, I have placed multiple integrators. So an order M filter is simply a order 1 filter followed by or M rounds of an order 1 filter. So if instead of a single integrator, I put up multiple integrators, I'll get this. That is one way of approaching this problem. But that way, you will be, if you look at it in time domain, you will be left with this GT integrated multiple times, which is mathematically hard to follow, or which is intuitively hard to follow. If we talk about in the frequency domain, you simply filter out a portion and you are happy. Fine.
Okay, sir.
Yeah, excellent. So similarly, we define y2t as minus gt sine 2 pi fct. Okay. So what I'll get is git by 2 sine 2 pi, sorry, sine 4 pi fct minus minus plus, this is minus gqt by 2 1 minus cos 4 pi fct. I've skipped a step, but you could do that. And passing this through the same low pass, passing this through the same low pass filter, I get, what was the notation that I used earlier? Y1 bar t, Y2 bar t, Y2 bar t equals GQT. Fine. So this is what this is somehow. Yes, passing this through the same bandpass filter, I get Y2T as GQT, which is what I wanted. So this is how we dissect a signal into its components. I can actually draw a nice figure for you for this as well. So block diagrams are quite useful in communication systems. Cos 2 pi fct this. So this is how you dissect a signal, or this is how you break a bandpass signal into its components. Now, there is another way of looking at bandpass and low pass signals, or low pass equivalents of bandpass signals, which is the Hilbert transform. So, have you come across the Hilbert transform earlier?
So don't remember.
Doesn't matter. So if you don't remember, then maybe you haven't come across the Hilbert transform. So the good thing about the Hilbert transform is that unlike the Fourier transform and the Laplace transform or the Z, you have done the Z transform actually, which reminds me.
Yes, sir.
Yeah. So unlike the Fourier transform, the Laplace transform or the Z transform, the Hilbert transform is not moving from one system of coordinates to another system of coordinates. It's simply that the Hilbert transform of a signal. So Hilbert transform of a signal GT is denoted, or the Hilbert transform G hat T of a signal GT is defined as G hat T equals 1 over pi t convolved with GT. So this G hat T is the Hilbert transform of a signal GT. Fine, just take this definition. Now we'll now look at the physical significance of this thing. Now, if this is G hat T, what is G hat F?
One upon.
Sorry. So GF I write. Okay, so let's what I'll okay, so that I cannot do because sharing the screen from another computer will be problematic. But if you look at important Fourier transform pairs, you find that this,
So U of F.
not U of F, 1 over pi t. So this is nothing but, or
So
1
is
over
it
pi
some
t.
sign
Yes,
function?
yes, signum function minus j signum of f, a sine function. So the sine function is defined as this is the sine function or the signum function, and minus j. Okay, so I'll rewrite this. Everything else is good, just the selection of pen is problematic. Yes, anyway. So I'll erase these before uploading the notes. So I'll just cut it right now. Whenever I upload the notes, I'll make all the erase corrections. So minus j signum of f gf. Fine. So this now somehow have to move this aside. So whiteboard had this advantage of allowing me to select and move text. OneNote yeah. OneNote does not allow selection that easily. So we'll keep this here and just move down. So I'll write g of f again. Yeah, so this is buggy. Yes, now it's working. G hat of f equals minus j sine of f gf. Fine. Based on this, I write, let's say I define a signal g plus of f. This g plus of f equals, let's say I define it as plus fine. This equals,
Sir, we have G and G hat of F,
sorry,
or both like they are supposed to be G and G hat.
yes, this is g of f, this is g hat of f.
Okay.
And we define g plus of f as the sum of these two. Fine. So this equals, so half gf, this minus j and plus j cancel out, plus sine of f gf. So equal to gf f greater than 0. Fine. Equal to equal to 0, f equal to 0, equal to z, or f less than equal, sorry, equal to half, equal to 0 when f is less than 0, and equal to gf by 2 or g0 by 2 at f equals 0. Fine. This is okay.
Yes, sir.
Excellent. So now what do we do with this? Now this I can write as, with the exception of f equal to 0, with the exception of 0, that's a single point. So we choose to ignore that. So I can write g plus of t as GT plus J G hat T. Fine. And this, so from what we have seen, this is real valued. And but G plus T is complex valued. Also, the Fourier transform of G plus T given as defined fine. This is okay.
Yes, sir.
Now, the fun thing is that you can see that this is simply rather F plus FC. So this is one other way to develop the complex low pass equivalent of a signal via the Hilbert transform. Equivalently, G plus T equals half of delta T plus J over pi T convolved with, oh sorry, GT. Fine. And if also GT equals real part of G plus T equals real part of fine.
So,
Yeah.
so I have a doubt. How exactly did G plus of F plus FC came out? Just a few moments back, because we were G plus of F is equals to G of half of G of
See, G tilde.
yeah,
This is
G
G.
tilde, yeah, how exactly this G tilde F plus FC came about? Because
So this was by inspection actually. This was simply that G plus of F. So this might be, there might be a minus sign. So if you have a, sorry about this. So this, this thing is, this is annoying actually. I cannot erase anything. Anyway, I'll write it here.
say you don't have to write it, just explaining it would be enough.
Yeah.
Like
So yeah. So I need to draw actually. So
like the from the equation it was G of F plus half of G of F plus signum of minus J signum of G of F, right? So how exactly it came about G tilde of F plus F? So that is the
see,
only issue.
yeah. So that's what I'm explaining. It's easier to explain it this way rather than derive it. You can
Okay.
derive it, that's longer. So what happens is that fine, this is GF.
Yes.
Now G, if I consider only this part, sorry, if I consider only the part covered by red, this thing, this is G plus F, fine. This gets
Yes.
deleted. And if I look at, this is G tilde F, right?
Yeah.
So G tilde F equals G of G plus F minus FC.
So the FC
This,
is the center of G plus F.
yeah, FC is the center of G plus F.
Okay.
Fine.
Yes.
This we had defined yesterday that FC is centered. So G is centered around plus and minus FC.
Okay.
Because of that, G plus F is centered around FC. Fine.
Mm. Yeah.
So this is how you define band, or this is how you define these things in terms of bandpass systems. Or the last topic related to the properties of Fourier transform that we'll cover are bandpass systems. So, or low pass equivalents of bandpass systems. Because we anyway derived the definition of bandpass signals from bandpass systems or bandpass filters. So whatever we have developed for bandpass signals, let's try to apply it back. So consider bandpass system HT centered around a frequency FC centered around a frequency FC and being and having a low pass equivalent, or let's not use the word low pass equivalent right now, because we'll see that the low pass equivalent of a system is slightly different from the low pass equivalent of a signal FC that can be expressed in the form ht equals real part of j. Fine. There is some h tilde t in which we want to express it as the low pass equivalent. So we are actually trying to find the low pass equivalent. Now we know that this h tilde t, this is low pass. Now yf equals hf gf, right, for an input signal. So since ht equals real of h tilde t power j 2 pi fct, this equals tilde conjugate h tilde t, sorry, h tilde t j 2 pi fct plus h tilde conjugate t minus j 2 pi fct. Fine. Half. Therefore hf equals half. Oh. Can you hear me?
Yes, sir. Yes.
Okay. Yes. So this I don't know whether OneNote crashed or the Teams app crashed, but I'm unable to. So the screen sharing suddenly stopped from my laptop, and since we are using I'm using an order one diversity. I'll tell you what order one diversity is later. So let's type the rest out. So
Sir,
yeah.
I have a doubt. This
Yes.
H tilde T and H star means conjugate of H tilde T,
Yeah.
they should be equal, right? In
Why?
magnitude.
No.
Otherwise, there could be shifting like d to the power j 2 pi fct is taking care of the shifting from the origin, but otherwise the magnitude should be same. Magnitude and other aspects.
Why?
Uh,
Why? Why should
isn't
these be same?
Otherwise the gain would be different, right? We require the gain to be same as well as the shifting to be happening.
I don't follow your point.
So the shifting is being taken care of by e to the power j 2 pi fct, right?
Yes,
And after along with the shifting we need to ensure that the gain is same for the pass band.
that's what we are trying to find out. Don't rush.
Okay.
Don't rush into conclusions. That's always a bad idea. So my laptop got stuck, so I'll type instead of writing, I'll type things here. So you can see whatever is left over, and I'll correct these. So I don't know, there is something wrong. So this crashed. So and we are slightly out of time as well. So we stop over here. What you can do is, since we'll start with amplitude modulation on Monday, and this is just 5 or 10 minutes worth of reading. So actually you can read section 2.10. So everyone has the textbook, right?
Sir,
What
which textbook?
Simon Haykin's textbook, I mentioned this. Okay, wait a second. What I will do is, since my laptop is misbehaving, wildly misbehaving, not simply misbehaving, it's not opening OneNote. So what I'll do is
Sir, could you give the information, the book and the section on the chat? That would be
yes,
easier
that's
for.
what I'm doing.
Okay.
Uh, so I'm stopping recording. So yes, anyway, so the book is Simon Haykin Communication Systems, 5th edition.
Sir, you have the PDF file or not?
Wait a second. So here's the official link of the book. Fine. And I want you to read section 2.10. Fine. Now stop recording.